So in this relationship, we are relating the position of a person moving and with the time. Okay, so that's our relationship. The position is going to be our dependent variable. The time is our independent variable. And the information we've been given is that person is traveling at a rate of 35 meters per minute. So since that is our rate and it's giving us the units of meters per minute, which is our dependent and independent quantities, that's probably going to be the rate of the problem, or in other words, the slope of the problem. We've been also given some coordinate which kind of fixes the position. So I'm just going to graph that coordinate first. Okay, so 7 and 1,000 meters is going to be right about there. Okay, so that's going to be our position. It's not necessarily our initial position though. So we want to be able to go back to the y-axis to get our initial position. Okay, so there's a few ways we can do this. We can use our rate. Okay, so I can use my rate of 35 meters per minute, and I can go backwards 7 minutes and use that 7 minutes to go backwards 7 groups of 35. That works out to be negative 245. And we can go back to 0 using that ratio. So it looks like it's going to be 755 meters. Okay, so that's one way we can do it. We could use our slope on our graph to do that. We can also use our equation, which is what we've been doing. So we have y equals, if we can recognize that this is in fact the slope, okay, we can plug that into our equation as 35x plus b. Okay, and then we can calculate our b value by plugging in our displacement and our time. Okay, and you can see that when we multiply that out, okay, there's our 245 meters that we're going to have to subtract. So b is going to end up being 755 meters. So we can, 755 meters is going to be somewhere around here, 600, 700, maybe somewhere around there. Okay, and we're going to have our straight line relationship. Our rate, constant rate of 35 meters per minute is going to give us that slope. And we can see that slope on the graph using that slope triangle here. So that's going to be plus 7 minutes plus 245 meters, okay, which works out to be 35 meters per minute. So there's our equation. So we've come up with the equation of the line, okay, of this line. We need to complete this table. So I'm going to maybe just go up by ones here. So 8 minutes is going to give us 10,035 meters. 9 minutes is 1070. 10 meters is going to be 1105. Okay, and that can give us 1105. It's somewhere around there for 1105. Where would that be? 1105 is somewhere right in there, which is about right. Okay, and again, that gives us our straight line relationship. For this one here, we're looking at some mass compared to volume. Well, mass compared to volume is density. Okay, when you talk about the ratio of mass to volume, we're talking about density. So we've got some samples of lead, and the container has an unknown weight. So that's container is going to be part of the mass that we calculate. So we're not going to get the full mass of the lead. So we have the amount of lead is 20 cubic centimeters, and it weighs in at 276.8 grams, and that's including the container. And we also have 59 centimeters cubed, and it weighs in at 719.06 grams, and again, that's including the container. So what we want to do is we want to figure out the density of lead. we want to know the ratio of density of grams to centimeters cubed. Well, that's going to be our slope. Okay, so let's first of all graph this. So we're going to have 20 grams, and that's going to be 276, somewhere around there. Okay, 59 grams, close to 60, is going to be 719, so maybe somewhere around there. Okay, so those are 2 points. Okay, we have some kind of graph that's looking something like that. I want to compare the change in the, okay, so I'm just going to maybe sketch a little table as well. So this is our volume in centimeters cubed, and this is the mass in grams. And we have volume is 2276.8. Here we have volume of 59, and this is going to be 719.06. Okay, so we need to work that out. Okay, to show the rise and run, or the slope, I need my change in y, which is going to be 719.06 minus 276.08, or sorry, 0.8. Okay, so getting a calculator for this, that works out to be, okay, 719.06 minus 276.8, and that's going to give us the difference of 442.26 grams. Okay, and that's over the run. Okay, so I'm just going to show that here. Our slope, our changes are going to be shown on the outside of the table. So 442.26 grams. Okay, and the run in this case is plus 29 centimeters cubed. Okay, we can show that on the graph like this. So this is going to be the change in x, which is 59 minus 20 equals 29 centimeters cubed. So then the slope in this problem, the slope ratio is going to be the change in the mass compared to the change in the volume. Or if we want to find the unit rate, okay, this is going to give us grams per centimeter cubed, which is in fact going to be our density then. So 442.26 divided by 39 is equal to 11.34 grams per cubic centimeter. Okay, so this works out to be, the slope works out to be 11.34 grams compared to 1 cubic centimeter. Okay, so that is the density of lead. The density is going to be the slope, so I'm just going to highlight that. So density is grams per centimeters cubed, so that's going to be my slope, which is going to be that right there. We also, it doesn't ask for it, but let's figure out the equation of this line, this relationship. We know we have the mass is equal to 11.34 grams per centimeters cubed times the number of centimeters cubed plus b. Okay, so b would then represent the y-intercept, or the constant in this problem, and that would represent the amount of the mass when there's no lead. So that's going to be our container mass. So plugging it in, we're going to plug in any pair. So I'm going to use 276.8 grams is equal to 11.34 times the number of grams, or number of cubic centimeters was 20, plus b. Calculating b, we end up with 276.8 minus 11.34 times 20, and we end up with 50 as our b value. okay, plus 50 grams. Okay, so my graph is a little bit inaccurate here. I should maybe just re-sketch this. So we're going to start at 50 grams and we're going to go up in a straight line pattern. That rate is our density rate, actually. It ends up being our density. The constant rate in the problem is density. And the starting point is going to be 50 grams, which is our container weight. So we get 11.34 x plus 50 grams. Okay, and there's our equation. Okay, but to answer the question, the density of this lead is going to be 11.34 grams per centimeter cubed, and that's going to be worked out by just looking at the slope part. The slope is our ratio, which is our density ratio.